Okay. Electric utilities design their systems to serve industrial, commercial, and residential loads. And what we want to do next is take some time to kind of examine the mixture of these loads in detail and how do actual physical devices that are out on the system correspond to some of these electrical engineering models that we've been showing previously in the class, right? Let's try to connect the circuit analysis to the actual devices that are out there in the system. And so we're going to look at utility load sectors and load types. The type of industrial load is going to vary mainly depending on the type of industry, commerce, and that are kind of prevalent in the area. Commercial and residential loads, however, are fairly consistent across the United States and consist of approximately the following load types shown here. 51% motor loads, about 19% lighting loads, about 14% power electronics, and about 16% HVAC, which stands for heating, ventilation, and air conditioning. So this is kind of the normal mix of what, if we were to break down the individual elements that are connected to the grid, what the different categories that they would fall into. We can see that residential overall, our homes make up about 36% of the load sector. Industrial users, aluminum smelters and manufacturers and things like that, they make up about 29% of the electricity consumption or the load devices connected to the grid. And then the commercial sector makes up about 35%. So although not ahead by a lot, residential is kind of like leading the pack. So we can see that it's really almost equal amongst the residential, industrial, and commercial classes here. Although motor loads too do tend to dominate the system, which kind of does explain a little bit about why we said earlier that the power factor of the grid is, looks inductive. For each of these load types, the load is going to behave differently in response to changes in the supply voltage, magnitude, and frequency. So what happens to these devices as they're kind of operated with deviations from normal supply? Since the frequency of the power system is typically fixed at 60 Hertz, of most interest is the voltage sensitivity of the load, which is often used by utilities to aid in system analysis of power flow, and what we'll later discuss is what's called stability of the system. When performing these analyses, utilities will estimate the mixture of loads on their systems, and then they'll build up an aggregate model of the load behavior by using what we call a combination of constant impedance, constant power, and constant current representations. The following table here, this table shows different load types, the approximate power factor of those loads, and sensitivity to the load to changes in real power consumption and reactive power consumption to the magnitude of voltage. Right? Since frequency is fixed, what usually we look at is how does the device's real power consumption change with respect to voltage, and what is the derivative of reactive power consumption with respect to change in the voltage. And we've just got some different elements here. So we look at electric heating. Electric heaters, as we've said previously, are mainly resistive. They have a power consumption that has a real power consumption that has a rate of change with respect to the voltage of 2. They don't consume any reactive power. Incandescent light bulbs have a power factor of 1, purely resistive. For every change in voltage one change in voltage units that they see, they get 1.5 changes in real power. Again, they don't consume any reactive power. Fluorescent lights have small inductors on them. Usually they have some inductive properties, so they've got a power factor of 0.9. They have a rate of change of power with respect to voltage of 1, and also a rate of change of reactive power with respect to voltage of 1. Motor loads, those have pretty big inductances on them, 0.8 to 0.9. They have a small, very small change in real power in response to a change in voltage. They will see a large amount of reactive power change in response to changes in voltage. And finally, we've got power electronic devices. Power electronics typically all have a power factor of purely 1. They don't respond really any differently to changes in voltage. They've got rates of changes of 0, no rate of change. A purely resistive load is, from an electrical engineering standpoint, is the simplest type of load. It's got no capacitive, no inductive reactance. The power factor of resistive loads are 1, as we showed on that chart. Power factor equals 1 of a resistive load, meaning that no reactive power is delivered or stored in a resistive circuit. So that should be pretty clear by now. Some examples of typical resistive loads include incandescent bulb, resistive heaters, toasters, an electric blanket, space heaters, electric ovens. We analyze resistive loads using Ohm's law and dissipate power according to the relationships P equals I squared R. Right? That's the resistive heating law. P equals IV. And P equals V squared over R. Right. As we can see from the formula V squared over R, power consumption will increase the lower the resistance is if voltage is constant. The smaller the value of R, the higher the power consumption will be. I.e., the strongest electric heater is the one with the lowest resistance, right? Or maybe we could put that in terms of a speaker. The more powerful the speaker is, the lower its resistance is. Typically, though, resistive loads aren't specified in terms of their resistance. They're specified in terms of watts. For example, a 60-watt light bulb. And that specification is usually done at the standard US utility voltage of 115 or 120 volts. Therefore, changing the voltage of the supply to a resistive load is going to change the power output in proportion to the square of the voltage change. Resistive loads are typically pretty tolerant of voltage fluctuations in terms of, device operation. They'll continue to still operate even if there's big variations in supply voltage, but they really can be damaged by high voltages. If you had a light bulb and you connected it up to 480 volts, for example, that would be too much power and the filament in the light bulb would burn up and you would destroy the light bulb. So they are typically sensitive to over voltage conditions. Purely resistive elements can be sensitive to over voltage conditions in that they'll overheat and wear out. They typically don't have that problem with low voltages. You can't put too little voltage on a light bulb, for example. It just won't light up. You won't damage it, though. They just simply consume less power, produce fewer lumen output. This behavior of purely resistive loads is kind of an important operational factor in the supply, because we don't actually supply 120 volts RMS. In the United States, the voltage tolerance at the wall is plus or minus 5%. So that means we can go from 114 to 126 volts. These are kind of the rules for operation. If I were to go measure the plug, I'm not always going to get 120 volts RMS. I'm going to get 6 volts above it and 6 volts below it, right? That's that plus or minus 5% tolerance. Another concept is that resistive loads are typically indifferent to frequency of the AC, and if I've got a purely resistive load and I wanted to operate it at, instead of 120 volts RMS, if I wanted to plug it into a DC supply of 120 volts, it would operate equally as well. So let's kind of demonstrate these properties of a purely resistive load using what I think is one of, at least now, one of the most common, maybe not in a couple of years. We've got a light bulb. It's fairly typical as a resistive load. Let's compare the power consumption in a 100-watt light bulb if it's operated at 114 volts, and then again it's operated at 126 volts. What's actually going on in this resistive element? So we have to kind of make an assumption here, is we're going to assume that the light bulb was rated at the US residential nominal voltage of 120 volts RMS. What we're then going to do is use that information and Ohm's law for a resistive circuit to calculate the resistance of the light bulb. So we've got R is just equal to V squared over P. Right, that's our power formula, rearranged to solve for power. It's 120 volts RMS. It was a 100-watt light bulb. That gives us, well, that's volts, and that's watts. That should be volts squared, but you know what I'm doing. Equals 144 ohms. So the resistance R of that 100-watt light bulb is actually 144 ohms. So now we can calculate the power at the plus and minus extremes of the voltage tolerance for the power system. So power, let's do the lower first. Power at 114 is just going to be 114 squared. We're just going to rearrange this, right? It's V squared over R. 114 squared over 144 ohms. That gives us 90.25 watts. And power at 126 is just 126 volts squared over the same resistance. Resistance doesn't change as a function of voltage, and that's 110.25 watts. So we notice that the 100-watt light bulb, if operated at a slower voltage of 114, is 90.25 watts. And if operated at a higher voltage of 126, is 110.25 watts. What that shows us is that the power consumption of the purely resistive loads change with the square of the voltage. Well, duh, right, you might say. This is actually very commonly exploited in what we would call the smart grid. And I haven't really mentioned smart grid technologies, but we're going to get into kind of new ways in this class that the grid is being operated. One of them is called volt control or voltage control. Why do we have a 120 plus or minus 5% voltage tolerance in the United States? Well, it is expensive. Historically, it has been expensive to maintain it within a tight tolerance. 5% is actually pretty good. You know, historically, it's been worse than that, 10% or somewhere about that. And in modern times, we've finally gotten to the point where it's kind of economically feasible to actually deliver 100, you know, between that 114 and 126. We can do it pretty reasonably. Some industries actually require for their equipment much higher voltage sensitivities, you know, plus or minus 0.1%. The semiconductor industry comes to mind. Well, from a residential level, what system planners have seen or noticed is, well, what if we could get everybody to operate 114 volts? Appliances are rated for 114 volts. You know, when they're tested and designed by the engineers who are building appliances, they have to run off 114 volt RMS because it's part of the US voltage standard tolerance. Well, from a power systems perspective, if I'm, as a utility, having trouble supplying electricity to the customer, what I can do is drop the voltage down to this low limit of 114, and then all purely resistive loads will reduce their power as a factor of the power reduction or the voltage reduction squared, which is really nice. It's called volt control. So physically what the utility is doing is they're going out to those load tap changers, they're reducing the voltage on the load tap changers down to the operational limit that gets you to about 114. They're a little bit higher, you know, usually about 116 to account for any sort of voltage fluctuations due to transients on the system, but they're operating you intentionally at that lower voltage level as a power conservation technique. Right? That's one of the ideas that's making up this concept of what we would call the smart grid, you know, new technologies that are influencing the way that the power system operates. So as we stated previously, electric motor loads in the United States make up about 50% of the total electric load. A motor, you probably already know, is a device that converts input electrical energy into mechanical energy, usually in the form of a rotating axle, so the form of rotary motion. They're used to drive fans, to drive pumps. They're inside of refrigerators, air conditioners, inside a lot of different power tools. They're in a huge variety of different industrial equipment, so it's a very, very common form of electrical load. One of the confusing things about motors is that despite the fact that they're driven by electrical voltages and currents, they're typically rated not in our customary units of watts and voltage and current, but instead they're often rated in horsepower. This is kind of a holdover from when electrical motors were first introduced into industry. James Watt, who was really trying to sell them, came up with the idea of rating them as according to how many horses they would actually displace. How much work could a draft horse be expected to do over the course of the day? So that's where that unit horsepower comes from, is, well, how many horses could this motor actually replace? And what James Watt determined was that 1 horsepower, that means how much energy or power could be delivered by a horse, is equivalent to 746 watts. So that calculation is actually a backwards calculation. It comes from how much energy can be extracted from a typical horse over the course of a week, and then how much energy can be extracted from a motor load or a motor over the course of the week, and then they went backwards and converted it to power. But this is what we use in modern engineering. The modern unit of a horsepower, which is almost never applied to actual horses, more often engines, right, is equivalent to 746 watts. And so now you know that that horsepower, it's a power rating, right? So a lot of times on these motor loads that you'll encounter when you're driving it, it'll say a 0.2 horsepower, and you need to know how many watts of power that actually is. And so you just multiply each horsepower by 746, and that tells you the power requirements of the motor that you're interested in driving. Usually those motors are stated, you know, that they run off a supplied voltage, you know, 480 volts or 230 volts and such, and then you can determine the current required of the circuit that it's connected to if you know the power requirements and the voltage that it's connected to. So that's how you would do that calculation. What we're more interested in here today, though, is looking at this motor that we have here. This is clearly not an actual motor. This is a circuit diagram that represents a motor. This is an electrical model of what we call the induction motor. So it's the most common type of electric motor, the induction motor, and it's got an equivalent circuit. And at this point in the class, we don't need to understand what all of these different elements represent in the equivalence circuit. What I really just am interested in showing you is that the operation of a motor, despite the fact that it's a mechanical machine that spins, can be represented using nothing but passive electrical components. In this case, you see inductors and resistors, and they're arranged in certain ways specific to the motor design and the type of motor. And we'll learn more about that in the course. But what I just kind of want to just put in your ear at this point is that motor loads can be modeled using passive electrical devices, inductors and resistors in this case. And we will get to this again in later detail in later classes, or in more detail in later classes. So an induction motor like this, it relies on an AC voltage source to create motion. You couldn't connect it. Most induction motors can't be connected directly to a DC supply. It needs to have a variable voltage AC. And the speed of the motor is directly related to the frequency of the electric supply. So speed of an AC motor is directly related to frequency of the supply, and the formula that governs that relationship is NS equals 120F divided by P. In this equation here, NS is called the synchronous speed of the motor. It's how fast it's spinning, and in this case it's measured in rotations per minute, or RPMs. No, it's in minutes, so that's kind of unusual, but rotations per minute. F is the system frequency of the AC supply, and P here is a new thing that's called the number of poles of the motor. Number of poles. And it's unitless. Poles refers to the number of magnet pairs that are in the motor. We haven't covered mechanical design of how motors or how generators actually work, but inherent to their operation is the fact that inside there are some magnets, and the speed of the operation, or the speed of the spinning, is dependent on the number of magnetic pairs inside of it. So that's P. It stands for the number of magnetic poles. So what we want to look at is first consider the effects of changing the electrical, well, we want to look at the effects of changing the electrical frequency on a fixed pole motor. So in this case, let's look at a motor that's got 4 poles, and let's consider the effects of changing the electrical frequency. So at 50 hertz, let's say, we would just plug 50 into here, and we're going to say a fixed pole of fixed number of poles of 4. So we do 120. The synchronous speed of the motor, and synchronous, is 120 times 50 hertz. So you can kind of see that the purpose of this 120 is conversion, and divide that by 4. Right. And that gives us 1500 RPMs. And then let's see what would happen if we change the frequency. So let's look at 40 hertz. NS is going to be the same, 120 divided by, or 120 times 40 this time. And we're going to divide that by 4. And that's going to slow the speed down to 1200 RPM. So what this equation shows us, and what the demonstration shows us, is that since the magnetic poles in a motor can't be changed, it's a mechanical construct. The method by which we can control the speed of the motor represented by the circuit is by actually adjusting the frequency of the voltage supply connected to it. But if the motor's connected to a 60 hertz grid like we have in the United States, how do we adjust F? Right? That should be fixed, 60 hertz constantly. Well, in modern times, we've invented a new device. It's called a variable frequency drive, a VFD, sometimes called an inverter, and it's used to convert the AC waveform into a DC waveform, and then convert the DC voltage that's rectified back into an AC waveform that has a different frequency than the original feeding voltage, than the frequency of the 60 hertz waveform that fed the VFD in the first place. So therefore, a variable frequency drive is what we would call a power electronic device that controls the speed of an AC motor, and it does so by varying the frequency supplied to that motor. The drive does some other things. It also regulates the output voltage in proportion to the output frequency, and it does this in order to provide a relatively constant voltage to frequency ratio, often called the volts to hertz ratio. You'll learn more about that in your courses on power electronic devices. That's really not the purpose of this. The design of such systems, we're more interested in the implementation of things like VFDs. The volts to hertz ratio is kind of an electrical requirement of the AC motor to produce a sufficient amount of torque, or the right amount of torque for the motor design. And you'll, like I said, you'll learn about that in other courses. But what we're interested in is mostly what are the impacts on the electrical system of using these VFD devices to control the speed of an AC motor. So let's look at this device, the variable frequency drive, in a little bit more detail. It really has two stages of power conversion, like I said earlier. It's got the first stage, which is a rectifier, and the second stage, which is an inverter. And somewhat confusingly, the term inverter is commonly used to refer to the entire drive. I don't do that personally. I call it a variable frequency drive, or a VFD, but for some reason, colloquially, inverter is a lot of times used to describe a variable frequency drive. The system kind of functions in the following manner. We've got a constant frequency, constant voltage AC power supply. In our system, this is going to be the 60 hertz power supplied to it. There is then a device called a rectifier. The rectifier is a circuit which converts this fixed voltage, which is going to be 460 volts, 600 volts, 4,160 volts. It's going to be the supply voltage of your electric utility, whatever you happen to be connected to. It depends on the size of your motor, what your constant voltage supply is going to be. And the rectifier converts that fixed voltage AC waveform. Remember, this is AC. This is sinusoidal right here. It's going to convert that into a fixed level DC supply, right? It's going to be a flat DC. You'll learn it's not actually flat, but it's approximately flat later on. But for right now, you just think that that's a flat level DC voltage, right? The inverter then takes the fixed DC voltage and it creates a output waveform of a different frequency. It creates a different sine wave. It does this using devices called thyristors or silicon-controlled rectifiers, and what they do is they switch the DC power on and off to produce a controllable AC power output at the desired frequency and the desired voltage. So there's a lot of times you see this in parentheses, it's called the switching section. And what this is doing is just switching the DC voltage that's supplied to the motor on and off really fast to recreate an AC sine wave. If you were to look at this closely, although it's called an AC sine wave, it really looks, it's got some kind of like digital nature to it. It almost looks binary if you look at it in a close enough resolution. Here we show that on some VFDs, on most VFDs I should say, there's a regulator, and what it does is it modifies the inverter switching characteristics so that the output frequency can be controlled. A lot of times it uses sensors, in this case we're showing a tachometer, to measure the controlled variables, which in this case is motor speed. So as I adjust the load on the output device, the tachometer is going to see how that affects, the change in load affects the RPMs of the motor. It will then send the speed signal through a controller. The regulator acts as the controller, and it will switch the value. In this we're showing it acts on the rectifier and the inverter, but typically what it does is it changes the switching algorithm or influences the switching algorithm in the inverter, which will then change the output waveform to bring that speed back up to what it was, or to reduce that speed back down to what it was before the load change, right? Why is this done? Well, in many systems, this load box is non-constant. For example, a pump used in an irrigation system they're often used to deliver different flow rates based on the time of day. And traditionally what has been done is different throttling devices such as dampers, valves, and different bypass systems have been used to reduce the flow rates. So I've mechanically changed the load by using throttling, some sort of throttling device basically. Although that method is effective, such devices are really not energy efficient whatsoever, right? You're using full power on the load and you're using a mechanical device basically to waste that energy. The use of a VFD, however, to vary the speed of fans and pumps during times when the motor-driven pump doesn't need to operate at 100% can therefore achieve significant reductions in energy use as compared to the traditional methods of using these mechanical throttling devices. And this is becoming an extremely common application of VFDs, is to replace these mechanical throttling devices. In these situations, we can kind of estimate the effect of the frequency variation of the inverter on the rotational speed of the motor, and therefore on the output torque and the output power of the motor. And the technique to do these are called these affinity laws here. So we use these things called affinity laws to calculate the relationship basically between frequency, rotational speed, output torque, and output power. These are commonly applied to pumps, fans, and hydraulic turbines. And we're going to just list the affinity laws for you. The first is that flow is directly proportional to speed, and the variable for flow in the affinity laws is Q. If you've taken thermodynamics, you recognize Q is often used as the heat flow. Well, in this case, we're just using Q as any sort of flow, typically water or some sort of gas. And that's going to be the rotational speed of the new flow rate divided by the new rotational speed of the old flow rate. So we see that flow rate and rotational speed are, in essence, cross-proportional. What about torque? Torque is proportional to the square of the rotational speed. So we could write the torque relations as new torque divided by old torque is equal to new rotational speed divided by old rotational speed squared. So this is flow rate, this is torque. And then the third one that we mentioned is power, right? And power is actually just to the third. It's the ratio of power to the ratio of, is equal to the ratio of speed to the third. So I'll just write that one over here. Power 2 over power 1 is equal to N2 over N1 third or cubed. In addition to the use of a variable frequency drive for energy efficiency, VFDs are often becoming more common because you could integrate them with a sensor and put them into some sort of feedback control system, building management system in manufacturing processes. So VFDs in a kind of a process control application is another thing that you might see these in. So the use of VFDs to save money on electric bills is probably the most typical application that you'll come across. And so let's perform an example to see how this is achieved using the affinity laws. So what this question is asking us to do is use the affinity laws that we just demonstrated to compare the cost to operate a 20 horsepower motor running at full speed for 365 days annually, 24 hours a day, to a pump driven by a VFD, which we can electrically throttle with the following schedule. We want to run it at 50% for 20% of the year. We want to run it at 80% speed for 50% of the year, and then the remaining time, which would be 30% of the year, we want to run it at 100% full speed. So using the VFD, how much energy can we save, and then therefore how much money can we save based on us being billed electricity at 10 cents a kilowatt hour. So we'll examine that relationship now. So although we didn't just present it, the general formula for cost is, we'll just take, well, I'll just write the word cost. How much you'll pay in electricity is just equal to power, right? That's your kilowatts, times how long it was on, which we'll just call run time, and then the rate, right? Electric rate. So this is going to be in kilowatt hours. Typically runtime will be in hours. And then the rate is your cost per kilowatt hour. Usually that's dollars per kilowatt hour. So we can see from our unit conversion not kilowatt hours here. Kilowatts, right? You can see from our unit conversion, if we multiply kilowatts by hours and then multiply that by dollars per kilowatt hour, we're just left with dollars, which is the cost. So the cost for running that 20 horsepower motor for 365 days a year, 24 hours a day at 10 cents a kilowatt hour. Let's do that calculation. So the 20 horsepower, right? Remember, this power's got to be in kilowatts for these units to cancel. So the first thing that we do is we convert 20 horsepower over to kilowatts. So we multiply by 0.746 kilowatt hours per horsepower. Sorry, kilowatts per horsepower, not kilowatt hours, right? That's a power conversion. We're just converting. This section of the equation is just converting horsepower, that 20 horsepower, over into kilowatts. We then need to multiply by the runtime in hours. We say we had 365 days, and there are 24 hours in a day. So we're converting, 1 year into hours. Then we were specified a cost of 10 cents a kilowatt hour. So we just multiply that by 10 cents, or $0.1. Multiply that all out. What we're going to find out is that the cost to run this 20 horsepower motor all year is $13,069 and 92 cents. So if I just turn that motor on, connect it to my electric supply and let it run, that's how much I'm going to spend in electricity to run a 20 horsepower motor for a full year. So what if we attach it to a VFD and we then throttle the speed to actually match the requirements of the load? To analyze those effects, we turn to the affinity laws. Clear my screen. So what we're going to look at is the power affinity law, which, remember, the power in the new circuit is equal to power in the old circuit, or is divided by power in the old circuit, is equal to speed in the new circuit divided by speed in the old circuit to the cube. Right? So what does that tell us? Well, I can determine how much power I save based on the rotational speed. So remember, what we said is that we can, because of the reduced load, we require reduced rotational speed, and we can back calculate the new power output, right? So what we're going to do is we're just going to rewrite this, solving for P2 in this equation. Very simply, we just multiply both sides by P1, and that tells us P2, the new power requirements of the motor, will just be equal to the old power requirement, 20 horsepower, times the ratio of the new speed to the old speed cubed. So at 50%, let's look at 50%, right? One of the schedules said that we can run the motor at 50% its rated speed. So we take our old power, 20 horsepower, and we multiply that by its new speed, which is 50 RPMs over 100 RPMs, let's say. Right? Really, I'm just using some numbers to show that this is a 50% reduction. What's important is the fraction inside there is 0.5. Now we have to cube it. And so that shows that the power drawn by this 20 horsepower motor, if it's only running at 50% rated speed, is going to be 2.5 horsepower. That's the new horsepower according to the affinity laws. We can repeat this for 80%. Right? That was the other speed reduction we saw. And in that one, we just multiply by 0.8 cubed, right? That's 20 horsepower times 0.8 cubed, and that's going to give us a reduction down to 10.24 horsepower. So if I run the motor at 50% of its rated speed, I'm only consuming 2.5 horsepower of power, and at 80% rated speed, I need to deliver 10.24 horsepower, as opposed to the 20 horsepower that the motor's rated for at full rotational speed. So now what we can do is we can use the schedule and these new powers to determine the effects on cost. So I'll just clear this slide again. At 50%, we take our new input power, which was 2.5 horsepower. Again, we need to convert the power over to kilowatts so that we can multiply it by our electric rate. So that's, again, 0.746 kilowatts per horsepower. So again, that's just a conversion. We now, we say, remember for the schedule, we said we're going to run it at 50% for we're going to run it at 50% speed for 20% of the year. So what's 20% of the year? Well, that's 0.2 times 365 days. That gives me percent of the year, 20% of the year in days. Now I need to convert times 24 hours to get it into hours. And then I just multiply by 10 cents per kilowatt hour. And that comes out to $326.75. 80%, it's a very similar calculation, right? The only thing we need to change is the input power and the percentage of the year that it's run at 80% speed. Remember on our last page we calculated that at 80% the engine's going to require 10.24 horsepower. So multiply 10.24, we do times 0.746 to do our conversion from horsepower to kilowatts. Now, from the schedule that we were given, we were running at 80% speed for 50% of the year, so times 0.5 times 365 times 24. Electric rate doesn't change, right? That's still 10 cents a kilowatt hour. We multiply that out, we get $3,345.90. So that's not the end of the calculation, right? 0.5 plus 0.2 is only 0.7. 30% of the year we're running at full speed, right? So we need to do our full speed calculation. 100% is going to be 20 horsepower times 0.746 to convert from horsepower over into kilowatts. This accounts for 0.3% of the operation time times 365 times 24 hours a day times $0.1 per kilowatt hour. Then we get $3,920.98. All right, so we've got three different operational costs depending on the horsepower and percent of the time that it runs based on the VFD. 326.75 for running it at 2.5 horsepower for 20% of the year. $3,345.90 for running it at 10.24 horsepower for 50% of the year. And $3,920.98 for running it at full speed or 20 horsepower for 0.3% for 30% of the year. So what we can do is the total cost for the year is we just add those three numbers up. So we get $326.75. That's for the 50%. Then we add $3,345.90 for the 50% of the year, and then $3,920.98 for the remaining 30% of the year. So that's my new total cost. The cost without the VFD was $1369.92. So I divide those numbers up and I get 58%, or I spent 58% of what I would have, or alternatively I could say that I saved 42% of my money using the VFD, right? So a very common application is percent savings, I guess we'll call that. Very common application is the use of the VFD to throttle a load electrically by reducing its speed to save energy when you don't need the full rated capability of the motor system. So consumer electronics are this last class of device that we're going to look at, and what they utilize are semiconductor circuits, and they make up radios, televisions, MP3 players, video recorders, DVD players, camcorders, computers, video game consoles, mobile phones. I could go on and on and on about devices that use semiconductors, and we call them consumer electronics, right? Nationally, it's estimated that such devices have basically accounted for about 10 to 15% of the electricity consumption in the average residential home, but the fraction for such devices is expected to increase, as estimated by this chart taken from the Energy Information Agency. So in these graphs, what we're showing is in 1980, 2005, and 2015, total residential electricity consumption. Clearly 2015 is a projected number, right? It's what the EIA thinks we're going to use based on previous increases. So it's a extrapolation. So this graph shows what we call the miscellaneous category, or this yellow category, growing to 34% of total residential energy consumption, which would be this yellow block represents 1.8 quads, just for doing things like plugging in your iPhone. Right? It's increased dramatically from 1980. You see that the total is, not even a full quad, maybe a quarter of a quad in 1980, and now we've got, it's almost 2 full quads. And this doesn't include, this does not include lighting and appliances, right? Although in this one it does. Actually in 1980, if you look, there's no green box, and I believe that this graph right here, that lighting is actually even included in that, where they've broken out lighting as its own block there. So, although exact figures are difficult to collect, there have been estimates made for annual U.S. energy consumption by device type. And although electricity consumption is going to differ between similar devices, we do have averages that exists for different device categories. And so that's what these graphs are showing. So this graph here on the left side is showing annual electricity consumption in terawatt hours for home entertainment and information technology category of devices. So we see across the entire United States collectively, in 1 year, TVs consume 65 terawatt hours of electric energy. Blu-ray players consume 6.5 terawatt hours of electric energy. Printers consume 1.3 terawatt hours of electricity. So although individually they don't consume a lot, collectively, just because there's so many of them, man, they really have some big impacts on the amount of energy that we consume as a society. Consumer electronic devices do. So remember, this is collective. This is aggregate information for the United States annually. On the right side of the graph here, what we have is unit electricity consumption. So how much electricity is consumed by a single unit over the course of a year. So for example, we look at if you have a monitor, if you go out and you buy a monitor, it looks like that over the course of a year, your monitor is going to consume 97 kilowatt hours. Now clearly different monitors consume different amounts of energy over the course of the year, and so this is kind of an averaged number. Video game consoles, 135 kilowatt hours. Computer desktops top the list of consumer electronic devices at 220 kilowatt hours, right? Your printer actually doesn't consume all that much, 12 kilowatt hours, things like that. And usually these are specified on the the rating of the appliance. But remember, this is for if it's always plugged in. So if you're the kind of person who unplugs your printer, for example, you wouldn't get quite that number. For these devices, one of the interesting things is that the active mode, when the device is actually getting used, about 76% of this number represents active usage. So 3/4 of this computer desktop usage is you sitting on the computer, doing processing, writing files and things like that. Idle, sleep, and off modes, depending how you define those, make up the other 25%. So you can turn your computer off, close the screen on your laptop, let it go into sleep mode. 25% of this 220 kilowatt hours is still being consumed in sleep modes and things like that. So while you may think your power or your consumer electronic devices are turned off, a lot of times they're still consuming a fair bit, about 1/4 of their total energy is consumed during that period.